I will begin with a word of prayer. Heavenly Father, we thank you for this day, and I thank you again for these students. Just pray you be with us today. Help us to learn a little bit more about your creation today, Lord. In your name I pray. Amen. I have an example for you guys. This one is what I was looking for in your book last time, but I could not find because it's not there. And so this is an example which is not quite as horrible as the one we worked on last time, which was good, but it's a good example we did, but this is a little bit easier to understand. So we did tangent of x. Last time we worked out that was x plus 1/3 x cubed, right, plus 2/15 x to the 5th, right? And we worked that out two ways. Well, I worked that out by long division last time, right? Now, this limit you could do with L'Hopital's, and you could do it. It's, I think, three applications of L'Hopital's gets it. But look at how you can do it with series. If you know the power series, in this case the Maclaurin series for tangent, we can replace this with the following. That's x plus 1/3 x cubed, right? Plus 2/15 x to the 5th plus and then we subtract x from that and divide by x cubed. So what does that work out to? Well, you notice what happens is we've got an x cubed that we could factor out at the top. That would leave us with a 1/3 plus 2/15 x squared, stuff like that, right? And then there's an x cubed downstairs. So you can cancel those. And the limit is immediately clear once you get to this, because we've got terms with x and higher, right? The single constant term in the series is 1/3, and so this limit works out to 1/3. So this is a good example of how we can use series to simplify limits that would be otherwise somewhat unpleasant with L'Hopital's rule. This one's not too bad. All right, so there's that. So you guys have any questions?
Are you taking homework questions?
Yeah, sure. I think I'm fresh out of calculational techniques. I've showed you how to find power series for pretty much everything. We've talked about error. We've talked about the proof of Taylor's theorem. We've talked about what is a Taylor series. We talked about interval of convergence, radius of convergence. I mean, I'm more or less out of tricks. There's a few things here and there I've missed probably, but that's kind of it. Yeah.
Section 9.8, question 20.
What is the actual question? Okay.
And this limit goes to infinity. And
interval of convergence of what?
Of
The sum of what series are we talking about here?
-1 to the n
-1 to the n
times n factorial.
times n factorial, yeah?
Times
X minus 5 to the n?
Over 3 to the n.
Over 3 to the n.
Yeah.
And that's n equals 0 to infinity.
Yeah.
Yeah, the interval of convergence of this one is just going to be 5. The singleton containing 5. Because there's an n factorial in the numerator. That's going to kill it. Now, to say, but the way we should understand that, right, is we should look at the absolute value of basically a sub n plus 1 over a sub n, so to speak. By that I mean, so when you take absolute value of the nth term, the -1 to the n goes away, right? So we get n plus 1 factorial times x minus 5 to the n plus 1 divided by 3 to the n plus 1 times 3 to the n divided by n factorial times x minus 5 to the n. Let me put my absolute value signs back in there. So I'm going to think about ratio test, right? I'm thinking about the ratio test. I'm calculating the ratio at the moment carefully. Now, what happens here is you get, n plus 1 times n factorial times x minus 5 divided by 3, right? Oh, and there's an n factorial down here. See, 3, I'm noticing that, 3 to the n plus 1 is 3 to the n times 3, right? So that's why I can just leave myself a 3. The 3 to the n's cancel. And in fact, if I was being a little bit lazier, I would have just canceled the n factorials here as well, right? So what we've got is n plus 1 divided by 3 times the absolute value of x minus 5. Right? This is what the ratio works out to. And so this goes to infinity unless x is equal to 5. So by the ratio test, the interval of convergence is rather boring. It's just the set containing just the number 5. The radius of convergence here is 0. So pretty much all of these kinds of questions we attack with the ratio test, almost without exception. Oh, I know there's one problem type we haven't covered yet. Here, let me do it. You guys think about your next homework question. I'll give you an example we haven't done yet. Find the sum of this series. N equals 0 to infinity of minus 1 to the n times 2 to the n divided by n factorial. What's that? Can you? Yeah, find the sum of the series. Like I said, this is a new kind of problem. It's not geometric. It's not telescoping in any natural, easy to see way. All right? So this is something else. And here's what the something else is. You just got to tilt your head and squint and go, you know what? This is really, if you look at it, this is really minus 2 to the n power over n factorial. And you know what? That is really the sum, n equals 0 to infinity, of x to the n over n factorial, parentheses, evaluating x it equals to minus 2. In other words, that's e to the x, putting x equals to minus 2, also known as e to the minus 2. These problems are just literally impossible unless you know your basic Maclaurin series, exponential, sine, cosine. It's usually what they're built from. On occasion, there'll be like a backwards geometric series or something, but all right. It occurs to me, I never did one of these for you yet. So there, don't say I didn't ever do anything for you. There's one. But I heard tell of another homework question. You guys had questions.
I have a question about 3, what we were talking about. It's 9.7, number 28. It's this one.
9.7, number 28, you say. All right. Here we're looking at f of x equal to the cube root of x. And he says n equals to 3 and c equals to 8, whatever that means. What does that mean? Well, his instructions, he says find the nth Taylor polynomial centered at c. So this basically just is straight application of the definition of Taylor polynomial. So this means we're supposed to calculate f of x, and here's the Taylor polynomial. It's going to be f of 8 plus f prime of 8 times x minus 8 plus 1/2 f prime prime of 8 times x minus 8 squared plus 1/3 factorial, otherwise known as 6, f prime 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 of 8 times x minus 8 cubed. This is the third order Taylor polynomial centered at c equals to 8. So all we got to do is calculate the derivatives and plug them in. This is just like finding a tangent line, right? Except instead of differentiating once, we had to differentiate a few times. And so doing, we can construct the best cubic approximation. So, I mean, I don't know. Is that clear enough? I mean, you know what to do? I mean, do I have to do it? I mean, I can work it out, but I don't think it's the best use of our time. Here, I'll give you another example. What if we wanted to find the power series for, let's say, e to the 3x centered at minus 1? Find power series centered at, I usually use x naught equals to minus 1 for f of x equals to e to the 3x. So here's how I do this. If I'm looking for a power series centered at minus 1, this means I'm looking for, I want an expansion in x plus 1 powers. So I just, you know, to quote a certain Star Trek captain, make it so, you know. So this is e to the 3 times, well, if I want x plus 1, make it happen. But if I do that, to be fair, I have to subtract 1. This is not the first time I've done this trick. It won't be the last. It's a good trick, though. And so this is e to the 3 times x plus 1 minus 3, right? Which by laws of algebra, this is e to the minus 3, e to the 3 times x plus 1. And then I fall back on my known Maclaurin expansion, the known power series expansion for the exponential. See, that's the sum, n equals 0 to infinity, of 3 times x plus 1, all to the nth power, divided by n factorial. Now, it's almost a power series, almost. But go back to my definition, we have to have in a particular format, so let me make that happen. So n equals 0 to infinity. We've got e to the minus 3 times 3 to the n divided by n factorial times x plus 1 to the power n. There you go. That is the power series for e to the 3x centered at minus 1. Now, you could have constructed that with the Taylor polynomial, like direct Taylor series, much the same, right? Like, alternatively, an alternative method, and maybe you guys like this more, I don't know, it's up to you. What's the nth derivative of x here? What if you differentiate n-fold times e to the 3x? You could actually do that without too much work, right? Just, but, well, almost, heart's in the right place. One more n. Yeah, 3 to the n times e to the 3x, right? So therefore, the nth derivative evaluated at minus 1 is 3 to the n times e to the minus 3. And from that, I have e to the 3x is equal to, by this Taylor's theorem, skipping over the analysis, of course, but 3 to the n, e to the minus 3 over n factorial, x plus 1 to the n. Taylor's theorem I've also written over here, you know. To construct the Taylor series, if it's convenient, if it's tenable, if it's possible, if it's not a pain, calculate the nth derivative of the function, evaluate at the center, divide by n factorial, and those are the coefficients to build the series, which is what I just did here. As you can see, my sneaky way and my brute force way gave the same answer. There are two different paths we can go down, but in the end, it's still the same road that we're on, you know? So, let's see here. Okay. Yeah. Surely you guys have another question before I make up more examples? Yep.
I just have a question on that one. I missed where you said you wrote one expansion with the x plus 1 powers. How did you know that centered at negative 1 was the one expansion that x plus 1 powers?
It's just the definition of power series. So if we have, you know, power series centered at x naught, what's that mean? That means it looks like f of x is equal to the sum n equals 0 to infinity, some coefficients, let's say c sub n, times x minus x naught to the n. I mean, this is what we mean by power series centered at x naught.
Okay, so it's just because it's negative, because it's subtracting.
Right, so minus a minus 1 gives me x plus 1, right? Example 4, you know, it wouldn't be hard to make the alternative method really sting a little bit. So if I just change this up just ever so slightly to, like, you know, x e to the 3x, then all of a sudden direct application of Taylor's theorem becomes rather, you want to differentiate that n times? I think if you play with it for a while, you can come up with a pattern. But goodness gracious, my method's easier. So, like, I would just say, well, that's, you know, x plus 1 minus 1 times e to the 3x, you know. So, you know, I can go from there. I just did plus 1, sorry. I'm just building off example 3 to do example 4 here. The point is, this exponential I can expand as those power series. And then I just have to put things together here. I have the sum n equals 0 to infinity of e to the minus 3, 3 to the n, x plus 1 to the n plus 1 over n factorial. Actually, this problem has an important calculational feature which we haven't faced yet, which is converting the summation variable to match up. See, I can't just combine these as they currently are constituted because I got n plus 1 on the first one, I've got n on the second one. So in order to combine those, I have to like change the variable summation. So let me suggest that we say k is n plus 1 on this one. Then if I do that, I have the sum k equals 1, I believe, because if n equals 0, k equals 1, to infinity e to the minus 3, 3 to the k minus 1, times x plus 1 to the k, divided by k minus 1 factorial. And then I can just put n equals k on the other sum. Of course, this is a different meaning for the k than in the first one. And now at least they have matching powers, so I can add them, but I got to be careful because this one has a 0th term, whereas that one doesn't. So I just peel off the 0th term, which is what? K equals 0 here gives me minus e to the 3, minus 3. And then I have plus the sum, k equals 1 to infinity, of, well, e to the minus 3 times 3 to the k minus 1 over k minus 1 factorial, minus e to the minus 3 times 3 to the k divided by k factorial, times x plus 1 k. Yeah. So we haven't, I think it's the first time I've really faced this computational complexity with you guys in class. But this happens, that we have to combine things like this. And you could simplify this. I mean, I can factor out things. I could clean that up. But I'm going to stop. That's enough on that example for now. Yeah.
I have a question on problem 4 now.
Aha. Problem 4 of what?
It's the same, oh, sorry, I mean, it's still 9.7, number 30.
9.7, number 30. Okay. Which was?
Same idea as that,
Uh-huh.
except it's f(x) is equal to x squared cosine x.
X squared cosine of x. Okay.
N equaling 2 and c equaling pi.
All right, let me work that one out then. So you just want to, you're just uncertain of your work?
So yeah, like I try to work it out, and I think that, are you supposed to use the cosine? Are you supposed to use the Taylor series for cosine?
No. This one's before all that. Here it's just brute force application of the formula. It's kind of the same idea as like finding a tangent line. I mean, so here we have f prime of x is 2x cosine x minus x squared sine x. And then f prime prime, which is all I'm going to need, is 2 cosine of x minus 2x sine x minus 2x sine x minus x squared cosine x. Product rule. Then I just have to evaluate those at pi. That's what I'm going to need to construct a Taylor series of that. Well, not series, excuse me, polynomial. Series of getting carried away. Now, I mean, I can, my next example, I can show you how to find the Taylor series for this centered at pi if you're interested. That would sting a little bit in terms of an example. F prime of pi. So what happens? Sine of pi is 0. Cosine of pi is -1. Minus 2 pi, yeah. So F prime prime of pi. So -2, 0, 0, plus pi squared, apparently. So now we have everything we need. We just build it, right? So here it is. Yeah, x squared cosine of x is approximately, and I also need to know, I also should check out what's f of pi itself, right? That's the 0th term. Right, minus pi squared. So we got, it's approximately minus pi squared minus 2 pi times x minus pi plus pi squared minus 2 divided by 2 times x minus pi quantity squared. There you go. That is the, right there, that's the n equals 2 centered at pi Taylor polynomial for x squared cosine x. That's all there is to it. Do not be scared. Do not confuse this problem with the much more onerous problem of finding the complete power series for x squared cosine of x at pi. Like, I mean, x squared cosine of x equals what? I mean, what coefficients do I need here? C sub n, if I put x minus pi to the n equals 0 to infinity, right? That's the question is, what are Cn? That's the question that I think you're thinking about, but that's not the question which is asked there. I mean, we have all the tools we need. We have all the toys that at our disposal to do that. I would just do this. I'd say, okay, well that's x minus pi plus pi squared. Call this thing f of x to give it a name. Name names. Let's see here, and then cosine of x minus pi plus pi. And let's see here. So that's got like an x minus pi quantity squared minus 2 pi x minus pi plus pi squared, foiling that guy out. And then this, what's cosine of x minus pi plus pi? It's cosine minus sine, right? But the sine term goes away because it's got a sine pi, so the adding angles formula on this piece just leaves me with cosine of x minus pi times cosine pi, right? Maybe let me save myself some writing and write that on the step above. So like this can be simplified as cosine x minus pi cosine pi minus the sine of x minus pi sine pi, but by the way, that's just minus cosine of x minus pi. So with that in mind, this is just minus the sum, n equals 0 to infinity, of minus 1 to the n, x minus pi to the 2n divided by 2n factorial. And then what makes this especially unpleasant is that to find the power series of this, I actually have to distribute to 3 different series and then think about how to combine terms. Some of these combine, some of these don't. Like these and those both contribute to the same kind of terms, whereas the x minus pi gives an odd series which gets added. So you can, when you work through the full, if you were to work through the full thing, but tell you what, rather than doing that, let me just kind of cut this down here and do a slightly simpler calculation. So we got pi squared minus 2 pi x minus pi plus x minus pi squared, right? And then I'm going to multiply by the this thing right here, right? The first two terms in that are just minus 1 plus 1/2 x minus pi squared. So I could multiply series and see what I get. If we're right, we should match your answer that we got over there, right? So what's the constant term? Right, that's the constant. Is there any other? That's it for constant terms. How about linear terms? This times this, I get plus 2 pi, plus 2 pi. Huh. I thought I had, where's my error? Is it here, or is it here? Here, 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 here. Where's the error? It was going from here to here. I made a mistake. When you think about expanding this and that, so I'm thinking of that as like a plus b squared. That's the pattern, you know? So that's a squared plus 2ab plus b squared. So I, for some reason, have invented a minus here. That was supposed to be a plus. That's all. And then, of course, then this times that doesn't give me plus, it gives me minus, which is what we found over there. Are there any other linear terms? No. What's next up? Next up would be squared terms, right? So we've got, if you look at it from here to here, we've got pi squared from this one, right? But then we also get, let's see, where was it? Oh, this times that, which is what? Minus 2, right? Because if I'm multiplying by 1/2. So there you go. That's in agreement with what we found by direct application. Now, you could ask the question, which is the better method? What do you guys think? If you're asked to find the first 3 terms in the Taylor expansion for x squared cosine of x centered at pi, what's the right way to do this problem? It's definitely that way. Very good, Josh. Right. It's definitely that way. What if you want to find the first 10 terms? It depends. It's probably this way. Differentiation, but then again, the multiplication, it's just complicated either way. It's just a complicated problem is what it boils down to. But these are tools in our toolkit which we can use if we understand them. Yes?
9.7 over 16. 68. Yeah. And it's proof that if the function is an odd function, then it's nth Maclaurin polynomial summation without powers of x.
So suppose we have f of x is equal to, what's an odd function? F of minus x is what? Minus f of x, right? Odd. Right? This is what it means to have an odd function. Now let's suppose it has a Maclaurin expansion, right? Power series centered at 0. That would look like what? Generically speaking, sum n equals 0 to infinity of a sub n x to the power n, right? All you got to do is just plug that generic series expansion into the condition for it being an odd function and work it out. It will force the coefficients to either be unconstrained or to be 0, depending on whether they're odd or even. Just plug that expression. All you got to do is just plug this into there and see what it means. Here, I'll get you started. So f of minus x is what? Right? But we can simplify that. How is it that that's Now what's that equal to? It's equal to minus f of x, right? Which is minus the sum n equals 0 to infinity of an x to the n. So how do we combine series? How do you add series? To add them, we have to have them match up. They have to have matching powers. So the example I did a little bit earlier today, I actually had to work at that because the one had n plus 1, the other had n. I had to reindex them so they both matched and were both x to the power k, x plus 1 to the power k. Now, I don't face any such difficulty here because they both have x to the n. So I can put this, and I can rewrite this. What this says is that the sum n equals 0 to infinity of minus 1 to the n a sub n plus a sub n, parentheses, x to the n is equal to 0. But what does that mean? This is true for all x, right? In the interval of convergence for this function. So it must be that those coefficients are all vanishing. So, this implies then that minus 1 to the n an plus an is equal to 0. Then you just got to think about the even and odd case and see what happens. Like, what happens if n is even? What happens? Minus 1 to an even power is what? Minus 1 to the 2? Minus 1 to the 4th? Minus 1 to the 6th? Yeah, it's 1, right?
Well, that's still an odd number.
What's still an odd number? Let's see here. If n equals 2,
Is asking for an odd function, not one that's a negative. Minus. This 1 to whatever power is still odd.
yeah. But again, what we're doing at the moment is we're trying to analyze what does this mean, this equation here? What does this mean, What does that say about the coefficients? That's a condition that the coefficients of an odd function have to meet. That equation is required of the coefficients of an odd function. What does that equation mean? If you look at n equals to 2k, which is to say n is even, minus 1 to the 2k is minus 1 squared to the k, right? Which is 1 to the k, which is 1. So the red underlined equation, let me give it a name. What is this?
Oh,
Yeah?
okay.
So star says that a sub n plus a sub n is equal to 0 for n even, right? AKA what?
Yeah.
Twice an is equal to 0. Bad news if you're even a sub n, right? I mean, you're 0. Maybe, I don't know, maybe you want to be 0. Some people want to be 0, right? No?
No, I get it.
Okay. On the other hand, if we look at n odd, what happens? If n is odd, this gives you a minus.
Then it adds up.
So minus a sub n plus a sub n, 0 equals 0. True, but useless. Right? So we get no restriction on odd coefficients. Almost the same argument can be used to show that if you have an even function, it has to have even coefficients only. All the odds have to be 0.
Actually, that's question 69.
Yeah. Which one?
The 9.8 number 80.
9.8 number 80. Somebody.
It's another proof.
Oh, proof. You guys are killing me here. Section 9.8, number 80. What? Prove what? This is actually, this is almost not a proof. This is kind of more of a problem in some sense. So we're given, I like this one a lot. This has often been a test question on my previous tests. If you're given the sum n equals 0 to infinity of like Cn x to the n has radius of convergence r, then I'm going to restate the problem. Find the radius of convergence for the sum n equals 0 to infinity Cn x to the 2n, right? Right, that's what it is, 2n. So, you know, to me, the interesting thing about this problem is that it focuses in on how do we understand radius of convergence, and you know, just how the radius of convergence is so tied to the coefficients of the problem. So, ratio test, what does it tell me? It tells me that the limit as n goes to infinity, right, of Cn Cn plus 1, right, x to the n plus 1 over Cn x to the n is equal to what? That's the limit. I'm supposed to have absolute values. Sorry about that. That limit as n goes to infinity of Cn plus 1 over Cn absolute value, parentheses, times the absolute value of x, right? That's the ratio test. Now we know that the series, what? It converges. It's given to us that it converges for, you know, less than, so this, we have that the limit as n goes to infinity of Cn plus 1 over Cn times the absolute value of x is less than 1 when the absolute value of r is less than r. See, I know that the series, that the power series converges when I have that condition for x, right? That's given. So my question then is, what does the ratio test work out to for, and like, so I suppose, sorry, consider the ratio test for the sum n equals 0 to infinity of Cn x to the 2n. What happens there? If we look at the ratio there, we got limit as n goes to infinity of, you know, Cn plus 1 x to the 2n parentheses n plus 1 divided by Cn x to the 2n, right? Which works out to what? So this Cn plus 1 over Cn, we've seen that before. And then that gets multiplied by what? Because the x to the 2n plus 1 becomes x to the 2n plus 2. The x to the 2n cancels, but we're left with the x squared there. So to get that to be convergent, what do we need? Maybe I shouldn't use x. Maybe I should use something else, you know? Because this x and that x are not, I mean, it's going to be this x and this x over here are apparently not the same one, are they? So we need this to be less than 1. If you just compare these, this is going to be true if what? The absolute value of x squared is what? So you see this? We have this is less than 1. Nathaniel, you got to look at this. This is less than 1
Yes.
if that condition is met, right?
Yes.
But over here we need this is less than 1.
Yes.
So by substitution, I just need that this is less than r,
Yes.
right?
That's what I was writing, actually.
Okay, very good, very good. I can say these words, but if you don't see me pointing at things, it won't quite gel. Now there might be a better notation to communicate this proof in, but that's essentially it. What's more fun is instead of doing like this, replace it with something like you've got, Cn times 2x minus 3 to the n. What's the radius of convergence? Or what's the interval of convergence for that, given the interval of convergence for the original one? That's a question I like to ask. If you look at my old tests, you'll find it. That should be in your homework somewhere. But then again, I'll get over it. It's okay. Well, guys, I welcome more questions tomorrow.